So these are some Pythagorean theorem examples that might be helpful to you. There's going to be quite a few, so you want to space your work accordingly. First of all, you should know that carpenters have been using the Pythagorean theorem and right triangles for a really long time to make sure that they've made a right angle. So one trick you can do to make sure that you've got a right triangle is from a corner, measure out 3 feet or 3 inches. And from the other direction on the corner that you hope is a right angle, measure out 4 feet and then mark it. And then use your tape measure to make sure the distance between those 2 points is 5 feet. And if it satisfies the 3, 4, 5, then you've got a right triangle. Because 3 squared plus 4 squared is 9 plus 16, which is 25, which equals 5 squared. So if it satisfies the Pythagorean theorem, then you have a right angle. Now, this has been known since antiquity. The Egyptians knew that a 3, 4, 5 triangle makes a 90-degree angle, and so they would have a rope and they would put knots in it and they would stretch it. And in fact, the Egyptian word for priest translates as rope stretcher, because they would use ropes to do all sorts of constructions to divide up land evenly along the overflowing Nile and to make their corners of their buildings perfect squares so that their walls stand straight up and down and so that the corners are right angles. So we're going to be taking notes on pages 35 and 36. We're going to be doing 10 examples. You do need to draw the triangles because that's a big part of this. So example 1. Here's your triangle. Go ahead and draw it. You can pause the video. You want to find the length of x. Now, I want you to notice that x in this case is along the hypotenuse. It is along the side that is opposite the right angle. Don't be alarmed by the triangle being turned around. Find your right angle and come out from it, and then the opposite side is your hypotenuse. So that means that these two are the legs, and the legs are pretty interchangeable when you're solving a problem using the Pythagorean theorem. You're going to just square the legs, add them, and then you'll get a sum. And then you take the square root of both sides, and you get the answer for the length of your hypotenuse. So in this case, our value for x would be 20. And again, you can pause the video to copy down the notes. Now, notice that 12, 16, 20, they make what we are going to call a Pythagorean triple, because they're whole numbers that make the sides of a triangle. Not all sides of a right triangle are going to be nice, pretty whole numbers. If you divide those numbers by 4, you get 3, 4, 5. So it's a multiple of the 3, 4, 5 triangle. We call the 3, 4, 5 a primitive Pythagorean triple. There are other primitive Pythagorean triples, but multiples of 3, 4, 5 come up a lot on questions on tests, standardized tests, and so if you can recognize them, it'll save you a lot of time. Now, I want you to remember what it means when we say we're squaring something, right? When we say that the Pythagorean theorem is a squared plus b squared equals c squared, we're saying that the square made on one side, using one leg as a side of your square, and another leg as a side of your square, that the area of this pink and this blue would add up to make this green area here. So if this is 44 and this is 33, the blue one should be the difference, that the blue plus pink equals 44. So hopefully you can recognize 33 plus 11 would equal 44. So this blue one would have to be 11 square units, whatever those units are, centimeters, inches, feet, we don't know. So keep in mind again that the side of the triangle is the root of the square. So the whole idea of a root is that it is the side of a square with a certain area. So in this case, I know my leg is 7 and my other leg is 3. I would go on about doing the Pythagorean theorem, but I would remember that I'm not trying to find the hypotenuse. In this case, I'm trying to find the area of this squared, or the hypotenuse squared. So I would do 3 squared plus 7 squared, which would equal 58. And I would stop, because that is the area of the square. The length of the side of the square is the root of the area of the square. That's where the word square root comes from. So try this one again. Set it up yourself. Pause the video to draw the diagram. Hopefully you recognized right away that this was a 3, 4, 5 triangle. Now I want to remind you that when we're solving a square equation like this one, x squared equals 9, that there are two answers, plus or minus 3. But when we're doing geometry stuff, the lengths of the sides of things are usually positive, so we can skip the step where we say plus or minus and just jump to saying that the answer is positive 3. Go ahead and pause the video to copy the diagram and try this problem. So 5 squared plus 12 squared would be 25 plus 144, or 169. We take the square root of both sides. Square root of x squared is x. Square root of 169 is 13. So 5, 12, 13 turns out to be another famous Pythagorean triple, as is any multiple of it. Like if you double everything, 10, 24, 26, that would be another Pythagorean triple. As soon as you have one Pythagorean triple, like 5, 12, 13, every multiple of it will also make another triple. Now, not always will you find that the sides are nice, pretty numbers. For this example, the side x, our hypotenuse, which is opposite this right angle, is going to turn out to be a kind of ugly number. So go ahead and pause the video, draw the diagram, and give this one a shot. 2 squared plus 10 squared would be x squared, because 2 and 10 are the legs. 10 squared is 100, 2 squared is 4, so we get 104. And when we take the square root of that, we don't know what we're going to get. It's not a pretty number. It's going to be a little bit more than 10, but in this case, the sides of this right triangle are not always whole numbers. They could be decimals. We can express them as a radical. We could leave it as the square root of 104. But generally, as you get higher in math, you're going to want to simplify the radical like this. 104 is 4 times 26. You can split that into the square root of 4 times the square root of 26, because I can take the square root of this piece. And so I'd get 2 root 26. But for most real engineering work, you would just approximate it with a decimal out to the thousandths place. This is the tenths place, hundredths place, thousandths place. That's good enough to build a lot of bridges. This simplified radical structure was much more common when people didn't have calculators and had to use tables of square roots in order to calculate things out. So this is very old-fashioned, and a lot of people have forgotten how old-fashioned it is when they insist that you still do this. A decimal approximation is quite sufficient. There are, however, some numbers that you definitely want to reduce as a simplified radical, and we're going to be looking at those in the days ahead when we look at special right triangles. Here's another example. Pause the video, copy the diagram down, and set this problem up. Now in this problem, don't miss the fact that x is now on a leg. The side that comes out from the labeled right angle is a leg. And this is another side touching the right angle, so that is another leg. If I'd come from the right angle out across to the one side that does not touch it, that is my hypotenuse. So in this case, my hypotenuse is 4, my legs are 2, and x. So 2 squared plus x squared would equal 4 squared. 2 squared is 4. 4 squared is 16. Subtract 4 from both sides. Take the square root of both sides. And you could leave your answer as the square root of 12. I'm okay with that. But if you want to simplify it, and this is one of those ones where you should simplify it because the numbers aren't that big, 12 is 4 times 3. 4 is a square number, so I can split it up into the square root of 4 times the square root of 3. I can take the square root of 4 and simplify this further to be 2 root 3. But if you're building something, you're actually going to just give me the decimal, sometimes rounded just to the tenths place. But this one is rounded to the thousandths. Tenths, hundredths, thousandths place, yeah. And you don't generally want to round things off if you're putting them in, say, Delta Math, where they give you a symbol for the square root, or Khan Academy, they'll give you the symbol for the square root. Rounding it off isn't accurate because this is an irrational number. Anything with a square root that doesn't have a square root It's an irrational number. This decimal goes on forever, infinitely long, with no repeating pattern. So this is just an approximation. That's why the equal sign got wiggly. This one I'm asking for you to give me your decimal to the nearest tenth. Pause the video, copy the diagram, and try this problem. So in this case, my legs are what's given, and my hypotenuse is the x that I don't know. 9 squared plus 3 squared is 81 plus 9, or 90, which equals x squared. Square root of 90 is x. You could leave it as a radical, or you could give it to me as a decimal to the nearest tenth. The first decimal place is the tenth. Notice I changed my equal sign into a wiggly equal sign, because this is a rounded off approximation of this irrational number that goes on forever. Now, sometimes we will be applying the Pythagorean theorem in much more complicated looking diagrams, but the math itself is not really that much more complicated. This is a square-based pyramid, so even though this doesn't look like a square on the bottom, we're drawing it at an angle with perspective, so it really is a square. This is 10. The slant height, they say, the slant height is 8. That's the height sliding if I rolled a marble down the side of the pyramid. That would be 8. That's not the same thing as an edge. This would be the edge of the pyramid. We're looking for the height straight up and down. And if this was a solid structure, we wouldn't be able to measure that. But we could calculate it if we measured the exterior bottom edge of the square and a slant height on the exterior of our pyramid. What you have to recognize to do this problem is that the center, if it's a perfect square, the height's going to come down smack into the center. So this leg here is exactly half of this side here. And half of 10 is 5. So I am going to use 5 for that leg. H is my other leg. H squared plus 5 squared would equal 8 squared. Do the math, subtract the 25, take the square root of both sides, and approximate the height of your pyramid by rounding it off to the nearest tenth. So you would know the actual height of the inside of this solid. Now, one other thing that I want you to record in your notes is some basic Pythagorean triples that get used a lot on standardized SAT exams, MCAT exams, LSAT exam, GRE exam. They expect you to know your Pythagorean triples. So 3, 4, 5 is the most famous and ancient of all of them. And these are just multiples of 3, 4, 5. They also work as the sides of a right triangle. 5, 12, 13 comes up often, and its multiples also work. I could have kept going with the multiples forever, but you don't really see them with the bigger numbers. 7, 24, 25 is another, more rare Pythagorean triple, and 9, 40, 41 is another. Now there are plenty of others. 8, 15, 17 comes to mind as another Pythagorean triple. But these come up a lot, and they also have a kind of a cool pattern. Let's see if you can spot it. In each triple, there are 2 odd numbers and 1 even number. In each triple, the smallest number is an odd number. And if I square that smallest number, how does it relate to the other 2 numbers together? Think about if I square 7, how does that relate to these 2 numbers? Or if I square 5, how does it relate to those 2 numbers? If you see the pattern, I want to caution you that it only works with primitive Pythagorean triples that have an odd number as its lowest number. But it is kind of cool.